Hello, this is a video on how to solve the second order linear non-homogeneous equations using the method of undetermined coefficients. And basically we know that the general form looks like this right here. And the reason I put this note is because if this were equal to 0, that would be a homogeneous equation. So we're going to focus on what it would be if it wasn't 0. So we know that the solution form looks like this. We have a complementary component, and then we have a particular solution. So we know that the complementary solution is the general form of the solution of the homogeneous form, and there's 3 cases. So we have distinct real roots, we have repeated roots, and then we have complex roots. And then this is what those solutions would look like. So the particular solution is what we're looking for, and we're going to use the method of undetermined coefficients. So the concept is, if g of t is a polynomial, an exponential, its sine or cosine, or a combination of any of the above, then we can kind of guess the general form of the particular solution. We just won't know right away what the coefficients are. So when we're looking for a particular solution for the equation, we want to make sure that it's linearly independent from the complementary equation, right? So if g of t is a polynomial such as t to the third power, then we want our particular solution to be to the same power. And if g of t was an exponential like the function e, then we want to make sure that the particular solution is the function of e times a constant. And that constant is represented here by a. And if g of t was sine or cosine, then we want the particular solution to have both sine and cosine because we need to take account for the derivative. So here's an example. We're going to use y double prime minus y prime minus 2y prime is equal to negative e of t. So the very first step is we're going to find the complementary solution by just setting the left-hand side equal to 0. And then here is where we turn it into the characteristic equation, which is r squared minus r minus 2. And then we solve for r, and we get 2 distinct roots, which is going to be 2 and negative 1. And then over here, I would just put what the general form would look like. So I just filled in my 2 for r1, and then I filled in my negative 1 to r2. And then this is what the solution will look like. It's c1 e to the 2t plus c2 e to the negative t. All right, so next step is to determine the form of the solution of the particular solution. So we're just going to say that it's going to be a to the t. This form does not overlap with the components of the complementary solution, so we don't need to do anything like multiply by t to make sure that they're all linearly independent. And then for the third step, we're going to take the derivatives to the order needed to plug into the general form of the problem, and then we're going to take those derivatives and plug it in, and we're going to do some algebra. And at the end, you get a equals 1/2, and we're going to plug that 1/2 into the particular solution, which is right here. This was the a to the et. And then we're going to put it all together, and then that's our solution. So here's our complementary solution with the c1 e to the 2t plus c2 e to the negative t. And then here's our particular solution with our a to the et. And that a is 1/2 here. And that's it.